Okay, today we'll talk about the derivative as a slope of a tangent line, and to use this concept to determine the equation of the tangent line and normal line to a curve at a given point. So at the end of this lesson, you should be able to associate the slope of the tangent line to a curve with the derivative of a function at a given point and to determine the equation of the tangent line as well as that of the normal line to a curve at a given point. Okay, I hope you still recall this graph that we use in the definition of the derivative, and that considering that we have points P and Q on the graph of y equal to f of x, connecting these 2 points would result to a secant line, the slope of which will be given by the ratio of delta y to delta x. Now, if we will move Q closer and closer to P, the secant line would be rotating towards the red line, which is the tangent line to the curve at point P. So if we will now investigate what the derivative dy dx is, as given by the limit of delta y over delta x as delta x approaches 0, then the limit of the ratio delta y over delta x, which is the slope of the secant line as delta x approaches 0, would just be the slope of the tangent line to the curve at point P. So at this point, we're looking at dy dx value evaluated at a given point on the curve to give us the slope of the tangent line to the curve at that said point. Okay, at this point, suppose that x of 1 is in the domain of function f. Then the tangent line to the curve of y equal to f of x at the point P with coordinates x of 1, f of x of 1 is the line with equation of y minus f of x1 is equal to m times x minus x of 1. This is using the point-slope form for the equation of the line, where m here is the derivative dy dx evaluated at the point P x of 1 f of x of 1, which is the point of tangency, provided that the limit exists. Okay, let us make use of this concept to work on some examples. So for our first example, we would like to determine the equation of the tangent line and the normal line to y is equal to negative of 8 divided by the square root of x at the point 4, negative 4. Now in problems like this, where we are given a point, we first verify whether this point is on the given curve. So what we do is, we would be substituting 4 for x and negative 4 for y, working on y is equal to negative 8 over the square root of x, or this will just be equal to negative 8 times x to the negative 1/2, where we will obtain negative 4 is equal to negative 8 times x to the negative 1/2. So verifying whether this is an identity, then we will have 4 to the negative 1/2 will just be a 2, and the negative 8 divided by 2 will give us a negative 4. So there we end up with an identity, verifying now that really this point is a point on the said curve. So at this point, we will work on the derivative dy dx as given by negative 1/2 times negative 8 times x to the negative 3/2. This is obtained by using the rule differentiating a power of x, or we can simplify that to just a 4 divided by x to the 3/2. So evaluating on the derivative value dy dx at x equal to 4, then we will obtain 1/2. 1/2 therefore is the slope of the tangent line at the point 4, negative 4. And working on the equation of the tangent line, using the point-slope form for the equation of the line, then we will get y minus negative 4 is equal to 1/2 times x minus 4. Or we simplify this to x minus 2y minus 12 is equal to 0. The equation of the tangent line. Now from geometry, the normal line is said to be perpendicular to the tangent line at the point of tangency. So that on this basis, the slope of the normal line will always be equal to the negative reciprocal of the slope of the tangent. And with the slope of the tangent line here given by 1/2, then the slope of the normal would just be equal to negative 1 divided by 1/2, or we have negative 2. With this, and using the point 4, negative 4, the equation of the normal line is still using the point slope form, would now be given by y minus negative 4 is equal to negative 2 times x minus 4, or we simplify this to 2x plus y minus 4 is equal to 0. Okay, let us now work on another example. This time, we want to find the equation of the tangent to the curve of y equal to 2x squared plus 3 that is parallel to the line 8x minus y plus 3 is equal to 0. In this particular example, we are given a different set of data. What we know here is the equation of the curve y equal to 2x squared plus 3 and that the tangent would be parallel to this line. When the tangent line is said to be parallel to the line 8x minus y plus 3 equal to 0, then the slope of the tangent line would be equal to the slope of this line. And as to the slope of 8x minus y plus 3 equal to 0, if we are going to transform the equation to the slope-intercept form for the equation of a line, then we will have y is equal to 8x plus 3. And from this equation, we can directly read the value of the slope of this line, and that the slope of the line is equal to 8. And since the tangent line is to be parallel to this line, then the slope of the tangent line also will be equal to 8. Now, knowing the slope of the tangent line, our next step would be to determine the point or points on the curve of y equal to 2x squared plus 3, where the tangent line will have a slope of 8. So what we do is, we work on the derivative, dy dx, and that will just be equal to 4x. And equate this to the slope of the tangent line, which is given to be 8. So we have 4x is equal to 8, and this will give us x equal to 2. And with x equal to 2, substituting that in the equation of y is equal to 2x squared plus 3, then we will have 2 times the square of 2 plus 3, giving us an 11. So at this point, we already know and we have located the point of tangency, and that point is the point 2, 11, and the tangent line will have a slope of 8. So the equation now of the tangent line would be, again using the point slope form for the equation of the line, we will have y minus 11 is equal to 8 times x minus 2, or we simplify this to 8x minus y minus 5 is equal to 0. Okay, to summarize what we have today, that the derivative of y equal to f of x at point P is equal to the slope of the tangent line at that point P, and that this is given by the slope of the tangent line equal to the derivative dy dx, provided that the limit exists. And with this, the equation of the tangent line to the curve at point P is given by y minus f of x sub 1 is equal to m times x minus x sub 1, where m is the derivative dy dx value evaluated at point B. And since the normal line is always perpendicular to the tangent line at the point of tangency, then the slope of the normal line would equal the negative reciprocal of the slope of the tangent line. Okay, so that will be all for today. I will see you in the next lesson.